One of the things that we want to be aware of is that the definition of a tangent line to a curve does not cover the possibility of a vertical tangent line. So we remember probably from a pre-calculus or a college algebra course that if we had a vertical line, that technically the slope of a vertical line is undefined. And so we wouldn't actually get those types of slopes from the limit definition. It would actually be undefined, or the limit would not exist. And here's an example. If you look at this graph, at the point C, we actually have a vertical tangent line. And if we investigate kind of what's going on near that point x equals to c, if you look at the limit or the slopes of the secant lines, what's going to happen is they're going to get steeper and steeper and steeper, and that limit will approach either a positive infinity or a negative infinity. And if that happens, then what that's telling us is that we have a vertical tangent line at x equals to c. This now brings us to the derivative of a function, which is closely related to how we worked the previous example. The limit we use to find the slope of a tangent line is also used to define two fundamental operations of calculus, that being of differentiation. The definition of the derivative of a function, so instead of looking at it and thinking of it as getting the slope at one particular point, if we think of the point as being our variable, let's call it the variable x, then we can calculate the slope by using this limit definition for the slope of the curve at any random point x. And instead of calling it m, we're going to give it a new notation. The notation we're going to use is f prime. This is read the derivative of f, or f prime of x, and it's the limit as delta x approaches to 0 of f of x plus delta x minus f of x, all divided by delta x, okay, when this limit exists. The derivative is a function of x that gives the slope of the tangent line to the graph of f at the point x comma f of x. It can also be used to determine the instantaneous rate of change of one of the variables with respect to the other. So what this derivative represents, this f prime of x, it represents the slope of f of x at x. It also represents the instantaneous rate of change of f at x. The process of finding the derivative of a function is called the process of differentiation. That's what happens when we start with the original function f. We apply this limit notation. We take the derivative, and ending up with f prime, that final function, that's the process of differentiating. We say that a function is differentiable at x when its derivative exists at x, and it is differentiable on an open interval a comma b, when it is differentiable at every point in the interval. We have some alternative notations you'll sometimes see. In addition, we will focus mostly on f prime of x. This notation here is what's called the Leibnitz notation. We will also use that a lot, especially as we get into applied examples. If instead of calling it like f of x equals, if they use the old school y notation, you'll sometimes see the derivative represented as y prime. If we have a function and we want to apply the operation of differentiation, we'll write it as d dx of f of x. And then a notation we probably won't use it all this semester, that's more of an operator style notation. You'll see like a d subscript x. That's the derivative of x of the function y. Let's take a look at example 3. We're asked to find the derivative of f of x equals x cubed plus 2x using the limit definition of the derivative. So first things first, I'm going to go ahead and I'm going to write this out. F prime of x this is equal to the limit as delta x approaches to 0 of f of x plus delta x minus f of x, all divided by delta x. Again, it's the same three key pieces we had from before. This is the limit as delta x goes to 0 And I'm going to try to, it's going to be a lot of terms here. We want to take our time and make sure we get everything plugged into the right spot. The easiest part, whenever we're using this definition, is the second part in the numerator. It's simply subtracting f of x. Here, f of x is defined as x cubed plus 2x. So it's going to be x cubed plus 2x that goes here. And the brackets or some kind of grouping symbol is absolutely necessary, because at the end of the day, if we're trying to subtract f of x, then we need to subtract every single term that's a part of it. So ultimately, that subtraction will be distributed to every term belonging to f. As is almost always the case, the thing that requires the most amount of work is coming up with this expression here. We need to find f of x plus delta x. So this one's going to be a doozy. It's going to be quite a bit of algebra. To find f of x plus delta x, everywhere we see an x, we need to put x plus delta x. Which is going to look like this. And now be very careful. If you want to expand something to the third power, recall that means multiply by that thing that's out by itself 3 times. So that's going to be x plus delta x times x plus delta x times x plus delta x. Here, just distributing the 2 in, we have a 2x plus 2 delta x. In order to do this multiplication, you would actually need to multiply them 2 at a time, get that answer, and then take that answer and multiply it by the last one. I'm going to skip that algebra. I'll let you all kind of do that on your own. But there's a shortcut trick called Pascal's triangle, and I might upload a separate video showing you all how to use it. Pascal's triangle is a kind of a cool trick. Whenever you have to multiply higher powers of like a binomial. But essentially, if you multiply this all the way out and you go through all of that algebra, what you should end up with will be the following. You're going to have x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed. That's from doing that part. And then we still had these 2 additional terms. We had the plus 2x plus 2 delta x. So that is our f of x plus delta x. That's what we need to plug in over here. So let me squeeze them all in here. We had x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed plus 2x plus 2 delta x. And now we're going to go ahead and distribute and see if we can simplify to take this limit. This is the limit as delta x approaches to 0. We have x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed plus 2x plus 2 delta x minus x cubed minus 2x, all divided by delta x. With that distribution, we do see that some terms will cancel. For instance, we have a positive x cubed and a negative x cubed. We have a positive 2x and a negative 2x. Those also cancel. So at the moment, we're left with the following. We have the limit as delta x approaches to 0 of 3x squared delta x plus 3x delta x squared plus delta x cubed plus 2 delta x all divided by delta x. In the numerator, every single term there has a common factor of delta x, so we can factor that out. If we factor it out of the numerator, we're left with 3x squared plus 3x delta x plus delta x squared plus 2, all divided by delta x. We now get the delta x that we factored out to cancel with our original delta x in the denominator. Again, that's good evidence to support that we're going in the right direction. And now the very next step, we should be able to go ahead and take this limit by plugging in 0 for delta x. So I'm now going to take the limit, so I cease writing limit. And everywhere we see a delta x, I'm going to put 0. And what we end up with is this is going to be 0, this is going to be 0. So we get the function 3x squared plus 2. So starting with the original function, starting with f of x equals x cubed plus 2x, we successfully found its derivative, f prime of x, which is equal to 3x squared plus 2. Okay. This procedure, I understand that for some students, might seem a little bit daunting, especially working with like a cubic function as we did in this example, but the more of them you do by hand, the easier it will get. Furthermore, we will not be finding the derivative f prime by using the definition, the limit definition in the entire class. Eventually, we will learn a series of shortcut rules that will greatly cut down on the amount of work needed and make finding the derivative much, much faster than this. Okay. Yet at the same time, it's this very definition, the limit as delta x goes to 0, of f of x plus delta x minus f of x divided by delta x. This is the definition that gives us everything that we're going to be able to do in the class. So we want to get used to it in this example. There will be 2 tops on the first exam, on the next exam, where you actually have to do this by hand. But then once we kind of move beyond this section, we'll start to focus on some of the derivative rules, and this won't be as much of a point of emphasis. But right now it's important. You have to know how to calculate a derivative by using the limit definition.